Hi students, in this video's lectures I'm going to show you how to solve statics problems in statics, and there are a couple of problems I'm going to solve it both in a two-dimensional and a three-dimensional. This would help you to understand coordinate system, sign convention, free body diagram, resolving forces in 2D and 3D, and also the equilibrium equations in static conditions. This is in this exercise I will show like a couple of two or three problems. Just to follow it very carefully, this would be a very helpful video lecture for you to perform well in the examination. So let us look at basically in a static equilibrium condition, the net force is zero. They express there are in 2D there are two independent equations in x direction, y direction. The sum of the forces equal zero, and the perpendicular parallel direction depends on what kind of problem we going to solve it. Look at in 3D, the sum of the total force acting on the system is zero because it is in a static equilibrium conditions. Look at that, F in the x direction, y direction, z direction, independently the forces are zero. Let me tell you that the above equations, the previous discussion, it's about you can apply this equation to the particles or body. Suppose yeah, if you are dealing with a rigid body in equilibrium condition, static equilibrium condition, you should satisfy not only that three equations in a space, you also satisfy external forces and moments are balanced. Will impart no translational or rotational motion to the body in a rigid body, static equilibrium condition. So the sum of the force, sum of the moment should be zero. So it will give us six equilibrium equation in a rectangular, or you can take any three-dimensional coordinate system, Cartesian coordinate system. So what I'm talking about a free body diagram. First of all, just look at the coordinate axis, x-axis, y-axis, z-axis. The forces, if the force is acting in the direction of y-axis, along that direction, it is a positive. Similarly, the forces acting in the z direction, this direction, is a positive, and the x direction, this is a positive. If this is act against this direction, from origin to x, it is a positive, origin to y is positive, origin to z is positive. But if it is in the other way around, if the force act from the y to origin or downwards, that is a negative direction. If it is from the x to the origin or away from that origin, that's a negative. And similarly, z to origin and opposite axis is a minus. That is means negative. You have to use it. Even the forces, whatever you see that in the sign convention, so the forces, if it is along the direction of the x, y, z direction, then it is a positive. It's against that, then it is a negative. Similarly, clockwise is considered as a negative. If the moment is creating a clockwise rotation, then it is a negative. If it is opposite that, and counterclockwise, that is assumed as a positive. So when you want, this is a sign convention, you have to be very careful on it. You can use any kind of sign convention, whether it is a right hand rule or left hand rule, but you have to stick to that because you cannot mix the sign convention. And the first step to draw a free body diagram, identify the particle, body or body of interest, draw a coordinate axis or reference axis x, y, z direction, and specify the sign convention. Draw the it is very important you specify, you just draw x, y, z and specify the which direction you are assuming as a force is a positive, which direction you are assuming as a moment is a positive. That is very important. Draw the particle or body or free body free of constraint. So first of all, you should remove all the constraint. Suppose there is a support, you have to replace that support with a reaction force. For example, you can draw a whole free body diagram, or you can concentrate part of that, a specific part, and draw the free body diagram for that particular part. So apply the external forces acting on it. Okay, when you remove the constraint, so there are external force acting on it, so you have to replay, you have to include that part of it, external forces which is acting on that boundary. Specify the dimension, angle, position in the coordinates. That's very important. So let us look at this the inclined plane. Here a block is sliding, it is counter by another block through a pulley. So it is connected to the pulley, frictionless pulley. So let us assume that when you start that, you try a XY direction. So specify that forces which is acting this way, this due to the weight of that. So you are replacing that with so there is a friction force, there is a tension in the string, so which is acting in the positive direction, friction which is acting in the negative direction, and similarly mg acting as a negative direction. So you have to do that both in x and y components. You look at this, there is a T bar and the mg which is acting, and so you have to which one you are taking as a positive or negative. You have to specify that. Once your sign convention is specified, then you can easily. So this is the part of interest. So you can replace that with the angle which is alpha, and this is a positive, this is a positive, so this is a negative. Then this could be perpendicular, in the opposite direction, mg and this minus y would be a negative. So you have to be very, very careful on specifying the dimension. So let us we start with a very simple case about rectangular components of the force in a 2D. In this figure, the force, you look at this y, x, these are the positive, and the opposite direction is negative. So F has been resolved into components Fx along the x-axis and a component of Fy along the y-axis. Fx are they called a rectangular component. So Fx, the I is the that the force is the vectorial representation. You should represent force by vector. It is a vectorial component. So f of x in the I is the direction vector, and y similarly j is the vector. So total force you can represent by fx I plus fyj. So if you take that, resolve this f into x direction, y direction, this the magnitude of that fx is equal to f cos theta, and fy is equal to f sin theta. These are the unit vectors and the magnitude is 1. So now you can resolve this into x and y direction. It's a component. So now the similar thing which we can look into the 3D in a space, basically force rectangular component. Now you can resolve this various angle. F is the force. Now you convert that what is the Fy, Fh. So this is how you represent. Fh is the horizontal component, Fy is the along the projection along the y-axis. Then Fx equal to Fh cos theta. So Fh is the horizontal, this one. So the Fx equal to F sin sin theta y direction cos phi. So F z is equal to Fh sin F sin phi sin y and sin phi. So Fy is equal to F cos y. So this is the way you can represent, you can resolve a force in space on acting on a particle into various Fx, Fy, Fz component. So now look at this another in a 3D space. If you know that if you project along the x-axis, that is the theta x, theta y, it is the angle between f and the y-axis. F and the x-axis is the theta x, and the fz is f cos theta z, okay, that is between f and z direction. You resolve this component, you take the cos of that, the total vector can be in a vectorial representation, force can be represented in a vectorial representation, f is equal to fxi fyj plus fzk. So these are the I, j, k are the unit vectors in the x, y, z direction. So now suppose if you know the only the force of the magnitude which is acting along the no in the in any direction from if it is acting from m to n, then if you know the position of m and n, you can easily find out the vectorial component of the forces. For this is a very simple. For example, you fix your axis. What is the m? X1, y1 is z1, n, x2, y2 is z2. Now you find out what is the dx, dz, and dy. So the difference of the y different coordinates. Now you can get the what is this no length, d is equal to dx square plus dy square dz square. So now look at that vector mn. Basically mn is represented by dxi plus dyj plus dzk. So if you want to find out a unit vector of that particular direction of this vector mn, so what you have to do that mn vector divided by the magnitude of that. The magnitude of that, we know that it is from the, it's a d. So now you substitute that, it is a you can get a force of the in the magnitude into the unit vector of that direction which is acting on the direction from m to n. We can get, if you know the unit vector, if you multiply with the unit vector, you will get these components of these fx, fy, fz. So you do the simple mathematics trigonometry. You look at the cos theta x is nothing but dx by d, cos theta y dy by d, cos z. If you add and square it up, it will become the unit. Basically what it says that it is the unit vector is a dimensionless quantity, so a dimensionless representation. So this way we can resolve. In fact, if you know the magnitude of the force and you know the unit vector which is acting which is on this direction, then it just simply find out the unit vector from the position vectors and multiply that with the force magnitude. You will get the resolved component of the theta x, theta y, theta z, that is fx, fy, fz. Okay, so that's how you have to go about it. Let us look at that simple problem. The tower which is tied by a cable tension from A to B. So that is, these positions are all well clearly defined. So this is the problem. Now what we are going to find out, what is the tension in the cable. So the vectorial component of the x, y, z component of the tension, and then you can find it out easily. What are the theta x, theta y, theta z of that force. So you look at that AB, that is the tension which is acting from A to B. You have coordinates. So you fix this origin at this position, that is the, you can take it as a O. So now you find out from O is 0, 0, 0. So find out this position A. A is basically you know that from the origin how much it is distance is moved. So 30 in the if you fix it 30 in the k direction, basically that is a negative of the z direction. Y, you know this is the x, this is the z minus z, this is the y. So you construct the you construct the now the dx component, dy component, dz component, find out from the origin, and you know that what is the AB. AB, the vector is nothing but dxi plus dy j plus dzk. So AB, the magnitude is nothing but, if you once you find out dx dy z, you can find it out that what is that quantity, the magnitude quantity. Now you know the vector, the magnitude of that. So it's very simple. What is the unit vector? Lambda. AB divided by magnitude of AB vector divided by magnitude of the AB. So now the force, you look at the force, we don't know what is that. It's the vectorial component. We know the magnitude 2500 Newton. from the problem. So if that it is the force, the magnitude of the force is I know 2500 Newton. Now what you have to do is F into AB vector divided by AB, that is a lambda. So you convert that, now you resolve that into F is equal to minus of that component f of x, this is f of x, this is f of y, that is f of z. So you can easily find out dx by d will give you cos theta x, dy by d it will give you cos theta y, dz by d will give you a sin theta y. We have this definition from this equations. So you can easily find out if only you know the magnitude of the force, you can find out the various vectorial component, resolved component, that just using a projection of the unit vector along the force, that will give you various component of it. This is the one of the simplest problem which I could discuss. So what I am going to do is this is the problem. There are you look at this diagram. There is a flying balloon, and it is tied through a string, and A, B, C, D. Okay, this is B, C, D, and A is this position. So the O is the origin. So the coordinates are specifically is given. P is the force which is exerted by the balloon. So that is the P which is acting in the positive direction of the y, and we have to find out what is the component along the different string from B to A, or A to B, A to D, A to C. So suppose if one component is given from the equilibrium equation, easily you can find out the other component. So I'll demonstrate for the one particular problem, then you can easily solve that the remaining problem. So force at AR, basically it's given in the AR, the tensions, the TAB, TAC, TAD, and a P which is acting that. P is equal to Pj, express all other force in unit vector ijk. Now let us look at that. First is the coordinate, and this is the origin, and A is you look at this coordinate, and now find out what is the AB, AC, AD. That is the vector, vectorial vector of that position, AB, AC, AD. So once you find out that, you find out the magnitude of that. So the vector divided by the magnitude will give you the unit vector. So the vector TAB is equal to magnitude of the TAB into the unit vector. You will get the three equations, TAB, TAC, TAD. So we know from the equilibrium condition that sum of the total force equal to 0. Also you have to understand that in the x, y, z direction, I, j, k direction, individually the forces, sum of the forces equal to 0. So if you substitute this value TAB, TAC, TAD, whatever we get it into the plus PJ into this equation, so what would happen, you equate the ijk component to 0, you will get it, because the TAB is known, TAC 479, TAD, okay, this is TAD, TAC. So you will get this is a D, okay. You just understand that P is equal to 1031 Newton, okay, 1031 Newton. So just remember that finding out the unit vector and projecting that unit vector along the force, magnitude of the force, it will give you the force vectors. Finally you have to add all these vectors, force vectors, and make it as 0, because it is in a static equilibrium, it is a tide that, so so it is in a static equilibrium, so it is sum of the forces equal to 0. Then you replace that with ij component individually, x, y, f of x, sum of the forces in x direction, sum of the force in y direction, sum of the force in z direction also 0. So this is how one should take these and approach and solve that. It should be a systematic. So you are using the sign convention, you are using the you are finding the unit vector and projecting that unit vector along this force and the magnitude of the force, and you finding out so using the equilibrium equation, so everything. So the sign convention, the free body diagram, here the free body diagram, you can basically you are replacing that with the full free body diagram. Basically you can replace that in this what is happening individually. You can deal it, but this better you handle this way, that would quickly converge the solution. So how I hope you understand that how to solve static the problems in a static equilibrium condition, whether it is a particle, whether it is a body in rigid body in a no space. So you can easily solve that using you know static equilibrium equation, force equilibrium equations, and moment equilibrium equation. Just simply apply this, and you will you can easily. But follow the systematic procedure in the examination. Follow these steps. First draw the coordinate, sign convention, free body equilibrium equation, and whether it is a rigid body, then you have to put if you have less number of equations, then you can. So I hope, dear student, you will do well in the examination solving this problem.